trailer. Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to the ESO Paranal Observatory. So just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the Paranal Observatory since 2010, and I am also working in many projects in astronomy outreach. And regarding my personal hobbies, I am interested in astrophotography. So ESO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So during this tour, you will have some time to send your questions or comments, and we will answer the questions later. But I am not alone. I am with the producer, Hector Salas. How are you, Hector?
Hi Farid, happy to be here once again. So I'll introduce myself. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related to the circumgalactic medium. We can think of this as the environment that immediately surrounds galaxies. And I've been a member of the team of guys for Paranal Observatory since 2019. I started while I was doing my master's degree in the University of Antofagasta. And today I'm the producer, so I'll be changing the pictures and the videos. But I will also be reading all your comments and questions. So if you have any doubts or you want to send any greetings, just please feel free to do so in the comment sections. And during the tour, we will give a couple of instances to answer any questions you may have. And with that, I think we can start the tour.
And thank you very much, Hector. So yeah, please remember you can send your questions or comments, and later we'll have some time to answer them. Okay, so we are going to start immediately. And the first thing I want to do is to help you to understand a little bit the place of our visit. So we will begin with some information about the European Southern Observatory, or ESO. So ESO is composed of 16 member states, as you can see in this picture. So the headquarters of ESO are located in Germany. And also Australia has joined ESO as a strategic partner. So in this case, Chile is the host state and the home of all ESO observatories. So from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories such as ESO to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is essentially to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So right now, you will see a picture with the three observing sites of ESO in Chile. So here we have the Chacnantor Plateau. This is the site of the ALMA radio telescope. So ESO is part of this place for radio astronomy alongside other international partners. Additionally, south of the Atacama Desert, at 2,400 meters above sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT, the New Technology Telescope, or the 3.6 meter ESO telescope. And this one specifically is using the HARPS instrument. And HARPS is an exoplanet hunter. And finally, we have the place of our visit, Paranal Observatory. So this ESO observatory is the home of the Very Large Telescope, or VLT, and this is the most advanced visible light telescope on the planet. So in the next few years, we will also have the Extremely Large Telescope, or ELT, and this will be the biggest visible light telescope on Earth. And also, the CTA near Paranal will be an array of different telescopes focused on capturing gamma rays. Okay, so now we have a better picture. So now let's travel to the Paranal Observatory. We will see an animation. So now virtually we are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago, specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. So this mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. Now, where is the ocean? Well, the Pacific Ocean is located below of the cloud cover over there. And why those clouds? If right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt Stream. This is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, keeping below the cold, humid, and basically bad air for astronomy. About the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. The clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, regarding other natural barriers around this area, we can say that about 200 kilometers to the east, we have the Andes Mountains, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking the clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So, this is one of the best places on Earth for astronomical observations. Okay, so right now we can change the view to have an even closer look to Paranal. So as you can see here, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. So this is the general view of this beautiful observatory. So please remember, the atmosphere in this place is extremely quiet. So this observatory is a true oasis. And you will see how in one of the driest deserts, we have a lot of life, and of course we have a lot of science. So right now, we will change the view because now we are going to visit the summit of Cerro Paranal. So as you can see in this new screen in front of us, we have the Very Large Telescope, okay, or VLT, its acronym. So if you see the amount of buildings, we have four giant domes here, but also we have other small and rounded ones. So you see, we have one rounded one here, we have another here, and we have two more here and here, okay? So it is clear at this point that the Very Large Telescope is actually not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. So here you can find in front of you the four unit telescopes or UTs, and each one with a primary mirror of 8.2 meters of diameter. So essentially the giant ones in your screens. And the other small ones, as I told you already, we have a few small ones. They are the auxiliary telescopes or ATs. So each auxiliary telescope has a primary mirror of 1.8 meters of diameter. Now, each UT, I mean the big ones, each UT has a name in Mapudungun language. This is the language of the Mapuche culture. They are natives from central and south of Chile. So here we have, for example, Antu, and Antu means sun. And the second one is Cuyen, and Cuyen means moon. This one is Melipal, and Melipal means four stars, but this is a reference to the Southern Cross constellation. And this one is Jepun, and this is a reference to the planet Venus. Okay, so all of them have, let's say, astronomical names. And regarding the small ones, I mean the rounded ones here, they are very special because they are mobile. They are mobile telescopes, so they can be moved using a rail system. Okay, so if you look closely here, we have a rail system here with different stations. Do you see? So we have 30 different positions or stations distributed on this platform. So essentially, they were specifically designed to work all together as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a short animation. Okay, so in this animation, we can say that the technique to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. Now, thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. So essentially, all telescopes are connected by underground tunnels, and the physical light is traveling there until they reach this single point of combination in the middle of the platform. I mean, the interferometry building. Okay, so after this explanation, we can come back to the main screen because now you will have the opportunity to visit one of the telescopes, specifically the UT3 Melipal. We can't enter all the telescopes, but don't worry about that because the four ones are identical in size and shape. So the only difference are the instruments inside. You can know more, of course, about the instruments if you visit the ESO website. Okay, so now we are going to enter to this big telescope. And here we are. So the first thing you can see is that this is a giant telescope, of course. In this picture, we are on the last floor of this telescope at the same height of the main mirror in front of us. So the mirror, I will do a close-up here. This mirror has 22 tons with 8.2 meters of diameter, as I told you already, and 17 centimeters thickness. This mirror was created from a ceramic and flexible material. The name of this material is Cerodur, and the material of the surface is a very thin layer of aluminum. Okay, so this is essentially not glass. It's a ceramic material with an aluminum cover, and also the mirror is concave. It's like a spoon, let's say. Okay. Now, because of this particular type of mirror, you need to understand that when the telescope needs to point to a different astronomical object, you need to tilt the mirror. You need to point this telescope to different positions in the sky. And because of that, because this mirror is so heavy, and we are talking about a concave mirror, just because of gravity, physics, this mirror um, can suffer distortions, deformations. So we need to do something to prevent that, to compensate that. Because if we have this kind of deformations in the primary mirror, you are affecting the quality of the final picture. So we need to do something to not affect the quality of our pictures. And at this point, I can show you something very important about this telescope, but I need to show you from this other perspective because I want to explain how we can preserve the quality of our pictures. So if you see, we are in a different picture here. I mean, we are at the telescope platform level, and I can show you basically the mirror from this different position. So you can see this kind of structure, this cell. So essentially the mirror is on top of this cell. And I want to show you something here because if I do a close-up, you can you can notice this kind of gray boxes, right? These kind of devices are very important here because the gray boxes are something called actuators. The actuators are a kind of piston, and we have 150 in total, controlled by a computer. They are part of a technology that we are using in Paranal, and the name of this technology is active optics. Okay, this technology was developed by ESO. It was implemented in first place at La Silla Observatory long time ago, and basically the pistons, the actuators, they are acting on the mirror during the observations in order to keep the optimal shape of the concave mirror, the concave surface. Otherwise, it could suffer deformations just because of gravity. And those deformations, as I told you already, imperceptible in a first view, could be critical in the result of the observations. So essentially, with the active optics, we are preserving the quality of our pictures. Okay, in order to explain how this telescope is working at night, um, I want to come back to the previous screen because we have a short animation to explain that. So in first place, we need to open the door. Of course, we have this a little bit exaggerated. But the first thing is that light from the stars is going to impact in the primary mirror, the concave mirror. The light will be concentrated and reflected to the secondary mirror, and the light will be reflected again to a tertiary mirror, and from there the light can go to one of the three different instruments. In this animation, the instruments are represented by this kind of red, blue, and green cubes. So the instruments will convert the physical light into a digital picture, okay, into a digital signal, okay, and this signal will be transferred to another place in this observatory, will be transferred to a control building, so the astronomers can take a look at the pictures from a dedicated control room. So if you see in this picture here, well, the primary mirror is here, of course, but in the animation, of course, you was able to take a look at the secondary mirror. The secondary mirror is this one, okay? Is this little mirror here. This is a convex mirror, and the tertiary mirror is located in the middle, but it's not visible here because we have this block in the view, but the tertiary mirror is there, okay, in the middle of the primary mirror. So the primary mirror has a hole in the center. Okay. Okay. And regarding the instruments, well, we can see one of the instruments right here. So this big thing is essentially an instrument. It's like a big camera. Is It's very complex, of course, and that's why we need some engineers to do some frequent maintenance every day. That's why you have some people here working. They are engineers, and they are working during the day to do calibrations, maintenance, fixing problems. So basically, they are preparing the telescope for the next observation night. So essentially, the work during the day in Paranal is for engineers, and the work during the night is for astronomers. Okay, so this is essentially the explanation about this telescope. Please remember that all the telescopes are the same thing. The only thing that is different are the instruments. So this is what happens in this place, and now I need to go outside because we need to move to the next location. um, I am going to go back to the VLT platform, and the next stop will be the control building. The control building is here. Okay. As you can see, we are in the same mountaintop, but this control building is at a different level. Okay, so in the control building, I can show you the control building from another position. The control building is this place, and inside we have the control room. This is the dedicated place for the scientists, and we are going to visit this place in a few moments. But before doing that, I don't know, Hector, if we have some time to answer some questions.
Okay, so we have a couple of greetings. So we have Animevero 206 saying hi, and Jesswell from Brittany also saying hello. And she has a question for you. Is what is your particular field, speaker? Are you more of an engineer or a scientist?
No, I am an amateur astronomer, but for more than 15 years, so I have been able to collaborate in research and outreach So actually, I have been able to collaborate in actor observations, professional observations.
Yeah,
But no, I am not a scientist by myself. I mean, not an astronomer.
yeah, but
But
we both together
yeah,
had observed um,
excuse me,
remotely.
sir. Yes, yeah, exactly. So I have been able to observe remotely with you sometimes, Hector. I think
Yeah, yeah, and also
doing.
at the University of Antofagasta telescope, we also
Yeah, yeah,
in
that's
person.
right. So essentially, when just to clarify something, when you want to work in astronomy, and for any reason you can do it as an amateur astronomer or a professional scientist, or for example, the case of Hector that he's doing a master's, sorry,
PhD,
PhD. So sorry.
PhD.
Um, so you have different ways to do it. Okay. Of course, Hector has more ways to do observations or other kinds of science. In my case, I have been able to do observations with remote telescopes, but in all cases the important thing is that we are able to contribute to science. And when I say contributions to science, I am talking about for example, a paper, a publication in a scientific magazine. So probably the most important thing for anyone interested in contribute to astronomy is to know that it's possible, even if you are an amateur astronomer or professional astronomer. Uh, so that's what can I mention for now. I don't know, Hector, if you want to say more about you also.
Okay, so in my case, I'm doing a PhD in astronomy in Germany, and I met Farid for the first time while I was doing my master's degree in Chile at the University of Antofagasta. Well, he was very much involved with the divulgation area of the astronomy department, and that led to him collaborating in the actual science by participating in the observations and some other things. But not to mention, there are some ways that amateur astronomers can collaborate in science. One of them is, for example, the Galaxy Zoo project, when in which you can go there and there are a lot of different projects where you can see pictures and help to classify them because we have way too many observations right now and not enough time to classify all of the images. Let's say. And also in variable stars, there is a lot of use for amateur astronomers to help quantify how much stars are changing.
Yeah,
So,
that's right. So yeah, that's it. You're correct.
so I hope that helps to clarify both the roles. But I don't see any other questions so far. So let me ask you one question. What kind of maintenance do we require for the observatory? That is one of the usual questions that we receive.
Yeah, this is one of the usual questions. So when we talk about maintenance, we are talking about, well, mainly maintenance of the mirror. So in order to explain that, I can show you again this telescope, and you can see that the mirror looks in perfect condition. And you need to understand that this observatory was inaugurated um, around 1998, more than 20 years ago. So in order to keep the mirror in perfect conditions, you need to do two types of maintenance. One of them is something like a simple maintenance. You need to do it once a month. And in order to do this, you need to um, rotate the telescope a little bit. And a couple of engineers, they are going to spread a carbon dioxide snow on the mirror. This is something like a foam. So this element will remove dust from the mirror because, well, we are in the desert, we have dust. And um, this element will remove dust, and because the mirror is tilted, the dust and the carbon dioxide will fall to the ground by gravity. So this is one of the ways to keep the mirror clean in general terms. And the other way is more complex, and you need to do it every 2 years. And in this case, we need to extract the mirror, all the mirror and the cell from this telescope, from this enclosure. So In this case, they are using a special crane, and you can see from this picture some yellow structure here, right? So you need to place the mirror in this platform, and at the ground level, we have a special vehicle. So this special vehicle will, let's say, receive the mirror and will transfer the mirror down to the base camp. So we need to basically move the mirror to a special facility, the mirror maintenance building, because the mirror needs a recoating. A recoating is a process when you remove the aluminum from the surface with some special chemicals, and you need to put a new layer, a new aluminum layer. So at the end of this process, you will have a mirror that looks like a new mirror because you have a new surface of uh, in the top of this mirror. So when this process is ready after 3 or 4 days, we need to place the mirror again in the vehicle, come back to the platform, and lift the mirror and reinstall the mirror in the telescope. So in this way, the mirror will be ready again for observations. So that's the process, and that's why, as I told you already, all the mirrors looks that they look like a new mirror because we have been able to change the reflective surface many times, even if the mirror is the original mirror. So that's I can say about the maintenance.
Okay, and we have one next question. Does ESO have a dedicated AI for sorting out the huge amounts of data, Sarah? Okay, that is a topic of active research where not necessarily only ESO, but teams of astronomers from different universities are working on how to do this. And it's not something that is solved at this point. And and you have like things from different ways of this. For example, you could have something that classify whether um, some image has a galaxy and which type of galaxy it is. But you would also have a different type of classify AI that looks for things that are moving among images taken in different times. So you could detect like comets, something like that. But this is an ongoing problem that, and certainly at some point we're going to have more standard AI tools specifically to classify astronomical images. But for now, is a lot of different teams are working on not just classifying the different sorts of data, but also extracting information like how far, if it is a galaxy, how far away it is, and things like that. I hope that answered a bit the questions. And with that, I think we can continue. And we're going to have a second round for answering questions. So please, if you have any more doubts, just write it in the chat. I will try to answer to the best of our ability.
Okay, thank you very much, Hector. And we are going to continue then. And as I told you already, we are going to move to the control building. So the control building is well, it's a very important place, of course, because here we have the dedicated control room for the astronomers at night. So we are going to visit this place right now, and here we are in the control room, and as you can see, we have several separated workstations. So this is basically like an office space, okay? And each workstation is basically well, the main purpose is to do all the remote operations for a single telescope. So, for example, this workstation belongs to the Melipal telescope, the UT3. So, only operations with Melipal are from here, from this workstation. And you can see we have several computers for different purposes, and you have a few people working here, usually two or three people, no more than that. We don't need a lot of people in this place actually. In the opposite place we have other workstation. This workstation belongs to the UT4, Jepun. So only operations with Jepun are from here. So again, you have some people working here in the computers, supervising things. Um, they need to work here all night from sunset to dawn, and but this place is of course very comfortable, and you are not exposed to the environment. It's warm, so it's very nice to work here. I want to show you the remaining workstations. Here we have the workstation 4 and 2. So again, the same thing. We have different terminals for different purposes. Some people here working. And in the last workstation here, this workstation is for Kuyen, the UT2. Okay, so you need to understand that all the telescopes, instruments, and systems explained before are controlled from here. So I want to show you this workstation in detail. I will access here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. So each night we have a telescope operator and an astronomer per telescope. So for example, you can see some people here, and this person specifically, this person now in front of you, is a telescope operator. Okay, so the telescope operator is in charge of the technical details and the movement of the telescope. So he is like the pilot of the machine. The ESO astronomer instead is in charge to direct the scientific observations, and this person will decide the next steps. So he is more like the co-pilot. So let's say that this person here maybe is the astronomer. So the observations are essentially performed by experts from ESO for scientists from all the planet. Okay, so this is essentially what happens here in the control room. As you can see, it's not a super big place, it's just an office space, but it's very important for the night operations. So now I am going to come back to the main screen, because at this point you have a lot more information about the observatory and the people working here. But now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean La Silla, Paranal, and Chajnantor, because scientific staff from different countries are using the ESO telescopes to study objects near to our home solar system, and also others located in the more distant places in our universe. So now we are going to explore a list of the top 10 discoveries from the ESO sites so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. Very, very interesting. But we have just one more thing, something like a bonus track. It's something not too recent, but very, very important. A team of astronomers was able to capture a few years ago the first picture of a black hole. So the Event Horizon Telescope, or EHT, its acronym, an array of 8 ground-based telescopes distributed on the planet and working as an international collaboration, was able to achieve the first direct evidence of a supermassive black hole. So the picture will reveal the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the constellation Virgo. This object is located 55 million light years from Earth, and its mass is about 6,500 million times the mass of our sun. Okay, so we hope you like the top 10. This was only a fraction of the discoveries thanks to the ESO telescopes and the scientific stuff behind them. So now we can continue, and from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. The moon is below the horizon, and the sky is full of stars. So here we can see a few objects, and I am going to show you in first place a very popular constellation just about the Antu telescope. Okay, this is the Antu telescope. So we are going to take a look at this picture right here, and we will find this constellation right here. This is the Orion constellation. It's very, very popular, easy to identify, easy to find in the sky. In the mythology, this one represents a hunter. So you can recognize this constellation with because of those three stars here, somewhat aligned, representing Orion's belt. And inside of Orion, and next to the three stars here representing Orion's belt, we have another very, very interesting object. This is the Great Orion's Nebula. This is a star-forming region, and it's very, very bright. It's very easy to see. Even with the naked eye, you can see this object like a distorted spot in the sky. So you can observe this nebula with small binoculars or a small telescope. Now, we are going to change the position a little bit. We are going to move from Orion, and I will go up because at some point we are going to find the brightest star of the night sky. And this star is Sirius. Okay, this is the name of this star. This is the brightest star in the sky, remember? And this star belongs to the Canis Major constellation. Canis Major is another constellation that is, in this case, represents one of Orion's hunting dogs. So essentially, the constellation of the brightest star in the sky is connected in the mythology to Orion. Okay. Now, if we come back down and next to Antu, we can find another interesting object just right here. And this object is a different kind of object. In this case, we are looking at the Pleiades. The Pleiades is an open star cluster located in the Taurus constellation. Okay. Now, the majority of those objects, the objects we have been observing here, are visually close to a specific area very populated with stars. So if you look carefully, you can see that all this area here is more populated with stars if you compare with this area or this area. Okay, this is because we are looking at one of the Milky Way arms. The Milky Way is our galaxy. Okay, and our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between the constellations Scorpius and Sagittarius. And you can see all this area from this hemisphere. Okay, so now we are going to move to another sector in the sky because I want to show you two spots in the sky. I want to show you the south horizon, and we are going to focus on those spots. Okay, so right here we have the Magellanic Clouds. This one is the Large Magellanic Cloud, and this one is the Small Magellanic Cloud. They are not actually clouds, of course. They are galaxies with an irregular shape. Both of them are visible to the naked eye in a clear night like this one. And this name, the the Magellanic Clouds, refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people have no idea about what a galaxy is. You need to consider also that those objects are only visible from the southern hemisphere. So you cannot see the Magellanic Clouds from Europe or from USA, from Canada. You cannot see those objects, so you need to be in the southern hemisphere to observe those galaxies. Now, another important area right here next to the Magellanic Clouds is the smallest constellation of the sky. I mean the Southern Cross right here. So you can see the cross is like tilted now, okay, but it's very easy to recognize the shape. Okay. So this is an easy constellation to find in the night sky. It's the smallest constellation, as I told you already. It's only visible in the southern hemisphere and is a good guide to find the south celestial pole. So this is a projection of the Earth's south pole. And during the night, the stars appear to revolve around this point. Now, in the northern hemisphere, the observers in the northern hemisphere, they are very lucky because there is a very bright star just next to the north celestial pole, and that star is Polaris. But in the southern hemisphere, we don't have any bright star near there. So our solution is to use the Southern Cross to guide our the position. So we need to extend the longer stick of the Southern Cross about 4.5 times. So we are going to do that. We are going to extend in our imagination this longer stick like 1, 2, 3, 4.5, and more or less like here is the south celestial pole. So this, if you take an astrophotography to this area, essentially you will see, I mean, if you have a long exposure picture, you will see many circles coming from here. Okay, so this is the projection of the Earth's south pole in the sky. Okay, so with this explanation, we are going to finish the visit to Paranal at night. So I am going to come back at the original place and I will switch to the daytime view because we have one last stop, and this last stop is the residence of the observatory. But in order to do that, I need to go down to 2,400 meters in order to visit this very special place, the residence. Okay, so I need to rotate the view because I need to move to the base camp of Paranal. Okay, I mean the place of it's something like a mini city actually, because in this place we have different facilities such as the rooms for contractors, we have some offices, we have the mirror maintenance building, we have the energy plant, we have all the necessary things to survive in this desert. But you need to understand that the people here is not living in Paranal, they are working in on a shift system. Okay? And I am going to show you specifically the residence right here. This is the place where the ESO staff can stay and rest. You need to access using this ramp. This facility is not underground, it's actually just taking advantage of the shape of the land. But this is a very beautiful place, and I will show you this right now. Because this is the home of the ESO staff when they are working in the Atacama Desert. So as you can see, the workers can enjoy here more humid air. They have a swimming pool, some green areas, and for example, they also have the restaurant here. All this Paranal staff can eat in the restaurant. The restaurant is over there. We have also a lobby. We have a reception. So it's very similar to a normal hotel, but it's only for the staff. Okay, that's the only difference. Okay, so We are going to finish the explanation right now, so we can dedicate the last minutes in case we have other questions.
Okay, we have one more question, and it's about telescope operators. So, what kind of degree do you need to become a telescope operator? Or what kind
Well,
of
the telescope operators are usually engineers, electronics, from informatics. Essentially, people who are familiar with um, programming, they need to essentially um, run some scripts to allow the telescope to move to different places. So essentially, the telescope is doing many things in automatic, and the telescope operator is in charge to supervise and to run some scripts and etc. So essentially, this person needs strong knowledge in informatics. Okay, um, but it's not necessary to be an astronomer. I know there is an astronomer actually working as a telescope operator, but normally is an engineer. This is.
And that's the last question that we have. We have a couple of other comments and some greetings, like from Chuyat Steve says, "Hi everyone," but no more questions. So
Okay.
that's it. We can just say our farewells. So
Okay, thank you. Thank you very much, Hector. So from my side, I remind you that all these visits, information, and pictures are available on the ESO website. And we have this kind of virtual tours every 2 weeks, so you are free to pay attention to our social networks to know when we will have the next tour, Spanish or English, Paranal or La Silla. Okay? So thank you very much again for your virtual presence. And on behalf of ESO, I want to say, well, thank you very much again, and see you next time. Bye-bye.
bye.